Assalamu alaikum, dear friends and students. In this video, we will discuss the solution of the assignment based on chemistry of alkynes. So, students, you were given four questions for this assignment. The first question was to draw the structure of the products that are formed when but1-ine reacts with each of the following reagents. So there were nine reactions uh, were asked when but1-ine is treated with these reagents. And here is the structure of the but1-ine. We have four carbon chain with a carbon-carbon triple bond at position number 1. So let us begin. The first reaction was but1-ine plus bromine 1 equivalent, because it was written 1 molar equivalent. So with 1 molar equivalent means uh, we have the same molar ratio between this but1-ine and the bromine molecule. So when the bromine molecule adds across the carbon-carbon triple bond, we have the breakage of that triple bond, and a double bond is retained, and we have the two bromine at the across of the triple bond. So it's a vicinal dihalide. And for the second reaction, it was two equivalents used for the bromine. So obviously the first step will remain the same, that is triple bond converts into the double bond with the two bromo on both sides of the uh, triply bonded carbon. But with the another equivalent, we have another entry of bromine molecule across that carbon-carbon double bond. So overall, we have two bromo at one carbon and two bromo at the other carbon. For the third reaction, it was the reaction of but1-ine with HBr, hydrobromic acid, when one equivalent was used. Here, hydrogen will be added to one carbon and bromine will be added to the other carbon. And the triple bond will be converted into the double. The only question arises is of the regioselectivity, that where H will add and bromine will add. There are two possibilities, whether we have the entry of H here at the terminal carbon and bromine here, or the vice versa. So as per Markovnikov rules, we know that the entry of the positive part comes to the carbon which has higher number of hydrogens. So here we have one hydrogen and here we have zero hydrogen. So this H positive of HBr will add to the terminal carbon, so that we have the bromine at the other position. And for the second equivalent, if we have for the same HBr, again the same strategy will occur, that here hydrogen will be added and the bromine will come to this carbon again. So overall, we will have the two bromine at the same carbon, a case of geminal dibromoalkane. For the fifth reaction, it was asked but1-ine when reacts with hydrogen gas in excess when platinum is a catalyst. And remember, with the term excess, it means the triple bond will not stop at the double bond, rather it will move to the single bond, and hence two equivalents of H2 hydrogen gas are used to have the alkane. Here you may also confirm that initially it was 4 carbon molecule, again it is 4 carbon molecule. The only difference is of the full saturation or the full hydrogenation. For the sixth reaction, it was asked when but1-ine is treated with sodium amide, which is also called sodamide, in liquid ammonia, and then treated with methyl iodide, what will be formed. So it's a two-step reaction. The first step is basically a deprotonation step, because the sodium amide is a strong base, and this alkyne, as we know, it is a terminal alkyne. With the terminal alkyne, it means the carbon-carbon triple bond is at the terminal of the chain, is at the end of the chain. So we have one hydrogen here, which is not being shown since it is a line engine formula. So the first step will be the abstraction of this acidic hydrogen using this sodium amide. So we will have the anion here at the terminal carbon. Then that anion will attack in the second step to methyl, and it will be an SN2 reaction, and this iodine will be displaced and methyl will be added to this terminal carbon, and we will have this product. So overall, it's a substitution reaction because the one hydrogen which was here, which is not being shown, but it is here, it has been replaced with the methyl group, which must have come from this methyl iodide source. For the seventh reaction, again we have the same strategy, that is to deprotonate this but1 in the presence of sodium amide and liquid ammonia. However, this time the electrophile is changed. It is not methyl iodide, but it is tertiary butyl bromide. Here, the substitution will not occur as it occurred in the sixth reaction, and the reason is that in the case of iodomethane or methyl iodide, there was no hindrance, and simply this acetylide anion attacked the carbon and iodine was displaced as we discussed. But in this reaction, this acetylide anion cannot attack this carbon and displace bromine, although bromine is a good leaving group, but there is no right trajectory to displace this bromine because there is a lot of steric hindrance, because this carbon is surrounded by the 3-methyl and a bromo, and this carbon was surrounded by 3 hydrogen and an iodo group. So hydrogen are obviously much less having the space. It was no difficulty for this acetylide anion to attack this carbon, but this time this carbon will not be attacked. So what will happen? This time, one of the methyl, because the 3 methyls are same, so any of the methyls hydrogen will be pulled off by this acetylide ion, and this acetylide ion will regain its starting material, that is this but1. And when the hydrogen of this any of this methyl group is abstracted, the bromine will also displace, and we will have a carbon-carbon double bond between the methyl and this carbon, and this alkene will be formed. So rather than having the SN2 reaction as it happened in the previous step, this time E2 reaction will occur, that is the elimination reaction, because this haloalkane will not undergo the substitution but the elimination reaction. And a good guide to remember when the substitution will occur and when the elimination will occur is that when we have a primary alkyl halide, a substitution reaction will occur because there will be no much steric hindrance. But when we have the tertiary alkyl halide with beta hydrogen present, elimination reaction will be favored. For the 8th reaction, basically it's a 3-step reaction. And again, the first step is same, that is the abstraction of this acidic proton through sodium amide. And the second step is methyl iodide treatment with the methyl iodide, that will surely give this product, the product of the 6th reaction. But one step is additional, that is for this intermediate, the hydrogen gas will be added, which is in excess. So what will be the product? So we have discussed when this triple bond is treated with the hydrogen in excess in the presence of platinum, we have the complete saturation or the complete hydrogenation. This carbon-carbon triple bond will be converted into the carbon-carbon single bond. So overall, we will have a 5-carbon chain, which is called the pentane. Starting material, it was 4 carbon. So 1 carbon came from this methyl source, and then this saturation occurred because of this hydrogenation reaction. For the last reaction of this question, it was asked when but1 is treated with ozone, O3 is ozone, and then treated with the acetic acid. And we know that this is the ozonolysis reaction and followed by the oxidation. So we will have the breakage of carbon-carbon triple bond. It's same as we discussed for the case of reaction of alkene. So when this carbon-carbon triple bond will break, we will have 2 molecules, 1 molecule for this single carbon source, this terminal carbon source, and 1 molecule for this 3 carbon source. How 3? 1 carbon, 2 carbon, and this 3 carbon. So because this CC triple bond is broken, so we have 3 carbon at one side, 1 carbon at the other side, and both molecule will be converted to their corresponding carboxylic acid. So the first molecule will be the formic acid or the methanoic acid, and the second molecule will be the propanoic acid or propionic acid. So that was for the question 1. Now come to the question 2, which is somehow tricky question. It says an alkyne X has the molecular formula C10H18 and has the following reaction history. So based on these three reactions history, we have to deduce the structure of alkyne X. And obviously, each of the three statements will give some clue that will bring us to the structure of alkyne X. So let us discuss each. Let us take the advantage of each hint to come closer and to our structure of alkyne X. And remember, the molecular formula for alkyne X is given C10H18. So with the first instruction, first hint that this alkyne X does not react with sodamide. So what clue could you get? And remember, sodamide is a base that abstract the alkyne proton, that is called the acetylenic proton. But remember, alkyne can have acidic proton only when the alkyne is terminal, that is the carbon-carbon triple bond is at the end of the chain. And since sodamide does not react with alkyne, it means we do not have the terminal alkyne. Other way around, we could say the carbon-carbon triple bond is not at the corner of the chain, but somewhere lying between, within the molecule and between the carbon chain between the terminals of the carbon chain. We had better say. Now take the advantage of the third clue first, then we will go to the second clue. Reaction with ozone followed by acetic acid gives two identical carboxylic acid. This is a very good information because from this information we may simply infer that alkyne X must be the symmetrical molecule with triple bond lying in the middle of the chain. Why am I saying this? So first let us take the case. These are the four possible structures of the alkyne having the molecular formula C10H18. But in all four, one thing is common, that the carbon-carbon triple bond is lying in the middle of the molecule. It is deliberate because when this carbon-carbon triple bond is broken through the process of ozonolysis, we will have the two carboxylic acids which will be similar, because when this is broken from the middle, we will have this pentanoic acid twice, same as for this. In this case, we will have this carboxylic acid twice, same for the third and the fifth molecule. So these four possibilities, there are only four possibilities to justify this condition C. If the carbon-carbon triple bond is lying somewhere left or the right, at the left or the right position, then we will get the two different carboxylic acid. So that cannot be the case. Now take the advantage of the second clue, which says when it is reacted with the hydrogen gas in the excess platinum, it gives 2,7-dimethyl octane as the product. So now let's consider, what if all these four alkynes are hydrogenated to afford the corresponding alkane? Which alkane is in fact the 2,7-dimethyl octane? This cannot be 2,7-dimethyl octane because there is no branching. This is in fact not the 2,7, it is 3,6. But the third structure is, yes, it is the 2,7-dimethyl octane, and obviously the fourth one is not. So now this is the end of the question, because with this information we have come to conclusion that the alkyne X must be this alkyne, this one, which is our answer because it fulfills all the three requirements. The first requirement was that sodamide does not react with this alkyne. Yes, it does not react because the alkyne carbon-carbon triple bond is not in the corner but in the middle somewhere. And the third condition was that upon ozonolysis it gives the two symmetrical carboxylic acid, and yes, when it is broken it will give you the two symmetrical carboxylic acid. It is only possible when the carbon-carbon triple bond is lying in the middle of the molecule. And with the condition 2, it says upon hydrogenation we get the 2,7-dimethyl octane, and this is the only alkyne that gives you the 2,7-dimethyl octane. And to be very honest, even if we were not given the first and the third hint, this only hint is sufficient to give us the answer of the corresponding alkyne. With this only condition, we may come to three possibilities, whether the triple bond here or the here or at here. With this condition, the condition B and the condition C, we may get our desired product. However, we have to take the advantage of all the three hints. Now let us discuss the question 3. It says starting with ethyne, give the synthesis route for the following 5 molecules. Topology. So let us synthesize propyne from ethyne. That's very simple. It will not take much time to discuss this. The ethyne, when treated with the sodamide, will have the carbanion here, the negative charge here. When methylated in the presence of methyl iodide, we will have propyne formation. For the second reaction, but1 was to be formed from the ethyne. Here, instead of using the methyl iodide, if we simply use the ethyl iodide, we will have this but1, because the sodamide will abstract this hydrogen. We will have this carbanion. This carbanion will attack this carbon, this alpha carbon. Iodine will be displaced. We will have CH2, CH3 with this carbon attached. So this is called but1. However, to make but2, we have to use the methyl iodide twice. The strategy is first to abstract the hydrogen, which is at the terminal of the carbon, a triple bond. Then we will have the methyl iodide to have this propyne, which we already made in the first reaction. And then let us use again the sodamide to pull this acidic proton, and again treat with methyl iodide to have the methyl at the other side as well. So 2 methyl at the across at the both carbons of this ethyne to have but2. For the synthesis of this but2 from ethyne, basically it is similar until here. When you treat the ethyne with sodamide and methyl iodide, you will have propyne, and then again you treat with sodamide and methyl iodide, you will have but2, as we discussed in the third reaction. The only additional step is to hydrogenate this carbon-carbon triple bond to the carbon-carbon double bond, and this is possible with Lindlar's catalyst, because this Lindlar's catalyst will give us the cis stereochemistry for the carbon-carbon double bond. So hydrogen but2 is treated with hydrogen in the presence of Lindlar's catalyst to have cis but2. And what Lindlar catalyst is, it's a combination of palladium, calcium carbonate, and quinoline. We have discussed about the chemistry of Lindlar catalyst in the video when we discussed about the chemistry of alkynes. However, to have the trans but2 from ethyne, the last step is not the treatment of hydrogen with the Lindlar catalyst. Rather, we have to use some other reagent, lithium, in the presence of liquid ammonia at very low temperature, and then upon acidic aqueous workup, we will have this trans but2. And remember, triple bond, carbon-carbon triple bond is converted into carbon-carbon double bond. We have 2 stereochemistry possible, whether the cis or trans, and we have different reaction conditions to come to our final product. The last question for this assignment was to complete this chemical equation by drawing the product. So now let us discuss the first reaction. A chlorine is added across this carbon-carbon triple bond. This triple bond will be converted into the carbon-carbon double bond, and 1 chlorine will add here and 1 chlorine will add here. A simple addition reaction. And with HBr, and remember its axis. With axis, it means it will add twice. We will end up with the carbon-carbon single bond here. So when this Br will add here and H will add at a terminal. Why am I saying this? Because the Markovnikov rule says the positive part of the addendum molecule attach where the hydrogen are more in number. So hydrogen will add here, Br will add here, another mole of hydrogen will add here, and Br here. So overall, we have the 2 bromine at this carbon and 2 hydrogen at this carbon. And this, for this reaction, sodamide will abstract this proton, and then this negative anion will attack this carbon, bromine will be displaced. So overall, this phenyl and CH2 have come in place of the hydrogen. It's a substitution reaction. We have already done this. If you just consider as methyl iodide or ethyl iodide in the last question, so we simply have the methyl or ethyl here. But this time we have the phenyl CH2 here. For the last reaction is ozonolysis, the breakage of carbon-carbon triple bond, and again this cyclohexyl and 1,2 carbon here with the carboxylic acid at the terminal and the propanoic acid for the second molecule. So that's all for the assignment based on the chemistry of alkynes. I hope you enjoyed solving the assignment and you also enjoyed watching the solution of the assignment that was given to you. Thank you very much.